So thank you everybody for joining us at this basically very first colloquium at Comenius University Faculty of Mathematics, Physics and Informatics. In the future, we would like to continue in this series of informal lectures. Basically, we are targeted to PhD students where we want to introduce scientifically interesting topics in popular but a little bit more advanced language than usual, and in this form to create kind of a community of PhD students who are not just working on their projects but also communicate throughout all of the faculty. So I think that's all that needs to be said from the organization side. And as a very first lecture, I would like to introduce you its speaker, Peter Maták. Peter was a PhD student here at the Department of Theoretical Physics here at the faculty, and now he's continuing in exploring the early stages of the universe, and his main interest is theoretical particle physics and quantum kinetic theory. The stage will be here, all his in a second. The last thing that I want to mention, if you do have any question, please write them in the chat or raise your hand and I will give you the word after the lecture. If you write them in the chat, I will read them loud and clear at the very end. Thank you very much, and from now on, Peter, the word and the stage is all yours. Thank you very much.
Thank you very much for the possibility to give this talk. So I would like to talk about the origin of matter in the universe, and hopefully it will be understandable for most of you. So this is the outline of my talk. First, and perhaps for the longest time of this lecture, for the longest part of this lecture, I will talk about basic introductory basic principles and concepts that are important to understand the physics at this scale. But then I will continue lecturing about elementary particles, what they are, what are the particles we know today, and then I will mention the terms kinetic and chemical equilibrium, which is related to huge numbers of particles, such as in the conditions in the early universe. There is a connection of these issues to the error of time and irreversibility in physics, and then I will continue introducing the cosmology and the basic principles of cosmology, the expansion of universe, the observations, Sakharov conditions, and how matter-asymmetry can be produced in the early universe. So the main topic of this talk, of this lecture. So to begin with, let us look at this sentence. Can you read it? This is one of my most favorite jokes because it can be written in this way. And this is not exactly quoted from the book of Professor Ladislav Kvas, which is one of my most favorite books, this one. But it is to a large extent inspired by what is written in the 4th chapter of this book. So language is a way we cut reality into pieces. And to understand this is an important part of understanding of all physics, all modern physics, I think. It's a good metaphor. Now let us look at this picture. It's taken from a speller book for primary schools, and there is a lot of stuff here. There are some people, some human beings, dog, house, tree, birds and squirrels. And we can talk about all these quite intuitively. It's simple. There are different layers of quality. There is a human in general, or human beings. There is a child, or in particular one little girl here. Perhaps she has a name, like Anička, or something like that. We can also talk about structure. There is a house, which has a roof or windows. There are roof tiles. And we can continue with the finer structure. We can end up with elementary particles. All this is language. We can use it in a natural and intuitive way. Why we do not assign a single words to some crazy composition of birds and trees. We can do that. But the storytelling in this way will be very, very complicated. So that's the reason why we do not do this type of thing. And the reason why we are so good in using language is probably the biological evolution, which is kind of optimization in a long time scale. There is different view on cutting the reality, which is not from the book I mentioned before. And this is the dynamical physical laws in physics. We can view at the reality in time. We can, instead of cutting of space and human beings and all the stuff in space, we can talk about cutting of space-time, identifying regularities and matching and predicting them in temporal evolution of physical systems. We can construct kind of the block universe where the time is used as a spatial dimension in the same way, not as a spatial dimension, but in a similar way. And such regularities can be matched to physical laws that allow us to match and predict what will happen in the future. An example of that is the most basic example and the first physical law of this type is Newton's law of motion, where if we know the force F on the right hand side, we can predict the evolution of the position represented by a vector of position r. I was talking about the intuitiveness of using the everyday language, like Slovak or English, doesn't matter. The intuitiveness comes from the fact that the words correspond to basic building blocks of the reality as we know it. But what about the physics at different scales? When we talk about universe, we talk about things that are on much larger scales, the stars, galaxies, galaxy clusters. These are much more bigger than we normally perceive in reality around us. And when we talk about matter, its finest structure has constituents at much smaller scales that are even hard to understand in classical terms. In other words, there is no reason in either of these cases for anything based on usual language to work. No reason to work. So it should be rather surprise when our description doesn't fail. It should not be an expectation. So what we can do is that we can at least try to build a consistent picture, as consistent as possible, and there still may be some kind of inconsistencies, some weird things included. How do we know which language, which description is the best for certain phenomenon? Because we at these scales, like at the microscopic scale, in case of elementary particles, we may have different languages, different kinds of description. And how can we know which one is the best, which one reflects the reality best, in the best way? So we imagine this kind of problem as written here. This is from the exercise classes from classical mechanics, the subject that is taught here at university in the first year of physics study. What is a gravitational force acting on a point-like particle inside a spherical surface of mass m? So this type of thing, there is a thin spherical crust of mass m, diameter r, as you can see, and then in the distance that is not labeled explicitly, distance is labeled by z. From its center is a point-like particle of mass lowercase m. What is the force acting on this point-like particle? So it's clear that from rotational symmetry in this direction there is no non-zero component. The only non-zero component can be just from symmetry in a radial direction. But we do not know the orientation. Does it point outwards or downwards? The particle is closer to the upper part of the sphere, but there is much more stuff in the lower part here. So let's try to denote the direction pointing downwards, and we can make the calculation in this case. And we can cut the sphere, the crust, into many pieces and sum up, which is done by simple integral. Can you see the result of this integration now? Probably not. Only those who know the result, because there is other way to do the thing. Now can you see it? I guess no. I was not able to see it immediately. And even now, not. It's 0. How can this happen? We have complicated intermediate steps. They are much more complicated. There is a lot of more steps in between. But the result is 0. Now we can do something different. We can talk about Gauss' law and intensity of gravitational field, denoted by k vector. From the symmetry of the situation, we can almost immediately, using the language of fluxes and closed surfaces, see that it is 0. And the reason is the spherical symmetry of this problem, and symmetry is the main suspect in most of cases where such miraculous cancellations occur. Next important principle. We are not in the center of the universe. Just imagine how beautiful the world could be if anyone in his or her life applies this idea. But this is not exactly what I wanted to say by this. The important thing here is that we should often abandon even the most natural expectation. Because the natural expectation is that we are the center of the universe. But giving this up will simplify the description of planetary motion. Before the heliocentrism, which is much older than Copernicus, it was already present in ancient Greece, I think by works of Aristarchus. But in Ptolemaic astronomy, there were epicycles, the strange cycles that were assigned to planets to explain their motion in the sky. By moving the center to sun, these epicycles are not needed anymore, and the description simplifies a lot. So the last sentence I have already said. An example from more recent times of the common wisdom that has to be given up is the mirror symmetry. I guess you have no idea who is here, because it is not Albert Einstein. Albert Einstein is here on the right-hand side. And the first picture was not him, it was his mirror image. But how it can happen that you are probably confused when you look at the first figure? First of all, we are very well skilled in face recognition, seeing faces even where they are not. This is the Widget Nebula. But the features we use to identify faces of known persons are mostly mirror symmetric. They have reflective symmetry to some extent, to large extent, depending on our constitution. So the mirror symmetry, the parity, or the left-right symmetry, or symmetry under vector to minus vector and vice versa, is expected to be conserved in classical mechanics, and indeed it is. When we have some mechanical system and we consider its mirror image, we will get still valid temporal evolution of such systems. We will not get anything weird. The same holds for electromagnetism at the level of Maxwell equations, even at the level of quantum electrodynamics. But the left-right symmetry or parity is broken by weak interactions, which was observed for the first time by C.S. Wu and her collaborators in 1957. She constructed an experiment in which the nuclei of cobalt-60, the unstable isotope, were aligned. Their spin, nuclear spin, was aligned in a single direction by magnetic field. And the electrons emitted by this beta decay were flying out of the nuclei in one direction, almost entirely in the opposite direction to the nuclear spin. And when we consider the mirror image of this, the spin, so-called axial vector, will not change in the orientation in mirror. but the direction of motion of the electrons will change. So this definitely violates the parity symmetry of the situation, which is caused by the special nature of weak interactions that was recognized at that time by Lee and Young, who were awarded the Nobel Prize later. So this is again an example of assumption that has to be given up or relaxed in order to understand the particle physics at fundamental level. Then I think this is the last fundamental principle that I want to talk about is linearity principle, the idea of linearity. Linearity is well present in Newtonian classical mechanics. We are used to superposition of addition of forces, the vectors. Imagine that we have some particle that we are interested in, the red one, and then there are some planets or some massive points that are acting on some gravitational forces, let's say, or electromagnetic forces, doesn't matter. So the dynamics will be given by the composition of these two effects, the linear composition. The same holds for electromagnetic fields given by Maxwell equations. These are complicated equations, but basically they are linear. And when we have two charges, the resulting electric and magnetic fields or forces are given by the composition, linear composition. But the linearity is destroyed when general relativity or quantum corrections are taken into account. Because in no way the effect two black holes have on a space-time is no combination of the two effects, no linear combination. It's completely different problem to have two black holes with strong gravitational fields and cannot be solved using the solution of one black hole and one black hole. Similarly, in quantum electrodynamics, we can compute an effective action, and we will get a 4-photon vertex, effective vertex, that will lead to nonlinear corrections to quantum electrodynamics, to Maxwell equations or equations of motion. So there is no linearity in the world, with one important exception. The quantum theory itself is linear, in a sense that the playground, the phase space, is linear. It's the Hilbert space, which is a linear space. And observables are represented by operators on this space. Of course, there are some approaches to make nonlinear generalizations of quantum theory. The most famous is that of Steven Weinberg, that is here. But in this generalization, a common problem is that causality may be violated, which is, again, it may be an assumption that has to be relaxed, but we don't know yet, I think. This is not my research, so I have no idea how it really is, but in general, I think the wisdom is that nonlinear generalization leads to causality violation, which is not something that we want to have in theory. So this is a summary of these basic concepts that I would like you to have in mind in the rest of the lecture. So we should take care of the language that we use to describe physics at the scales that are beyond our experience. Sometimes even the natural assumption has to be relaxed, and we have to be aware of the fact that linearity is an approximation, almost always. Now I will move to elementary particles briefly. This is a standard model, the list of the particles that are included there. The latest member of the family is the Higgs particle that was detected or discovered in 2012. And then the other members of this family are divided into groups here. So the purple group are the quarks. Most of the stuff here is made of quarks, up and down, gluons, and electrons, and neutrinos, all the families of neutrinos here. The quarks are massive. The same holds for all fermions, all these three columns. These are three generations of particles. First one is the up quark, down quark, electron, and electron neutrino. And then there are second and third generation. The quarks and charged leptons, mu and tau, are unstable in this generation. The situation with neutrinos is more complicated because there is some kind of oscillation and mixing between these species. But when we talk about matter in the universe, we mostly talk about up and down, and they composite state called baryons. I will talk about that. Baryons, which are protons and neutrons, that are very important. Then there is Z0 and W plus minus, which are the electroweak bosons. This is something that is closely related to the beta decay I was already talking in connection to the cobalt decay in the parity violating experiment. And these are carriers of electroweak forces. Can be, I can say, I think. The Higgs particle is important in the sense that it is related to the so-called Higgs mechanism and something that is related to the masses of particles. Okay. Baryons are composite states of three quarks, or antibaryons in case of antiquarks. Proton and neutron are the stable, almost stable examples. Neutron is unstable and decays into proton and electron and antineutrino by the weak decay in nuclei. But there are much more baryons which are unstable, and I think aesthetically nice are the pictures that are related to the unstable baryons that can be arranged into the root diagrams of the SU3 symmetry. This is a symmetry of rotations in three-dimensional complex space that preserves the orientation. And considering this symmetry between the first lightest three quarks can lead to this type of periodic table of these composite particles. This is similar to what we know for chemical elements, but at the level of strong forces. And these pictures are taken from Wikipedia because they were nice there. But mostly what we should remember that proton and neutron are the baryons. To get baryon number 1 for proton and neutron, each quark is assigned baryon number 1/3. And baryon number is conserved in standard model. So in the interactions between the particles listed before, the baryon number is conserved quantity, which means that having some kind of reaction interaction, the number of baryons at the beginning is the same as the number of baryons at the end. The same holds for lepton number. Each lepton, neutrino, or charged lepton like electron is assigned lepton number 1. How we describe the interactions of particles in particle physics. The language of particle physics is complicated, and this is quantum field theory, which is hard to be explained for a non-physicist. It's important to know that the basic vocabulary, like particles, position, velocity, is not available for interacting particles. We can use it in an approximative way. As an asymptotic state, we can talk about asymptotic states as particles. If we start with particles that are far away from each other in -infinity in time, and again, the products of such reaction have to be far away in infinity after the reaction, which is schematically shown in this figure. But what happens if we have some kind of ideal gas of plasma of such particles? Can we talk about particles then? Yes, to some extent. When the plasma or the gas of particles or the thermal medium in the early universe is dilute enough. So if most of the particles are far away enough, for most of the time. And they remember the quantum nature only when they approach each other and they interact by means of quantum field theory. Then we can use the classical kinetic theory, the classical statistical mechanics, for the description of these particles, which was founded by probably many people, but mostly by Ludwig Boltzmann, who lived in Vienna. And this is some nice quote that is relevant to this subject, which you can read probably. But the fundamental thing in this kinetic theory is the entropy function or entropy density that is written here. We describe the thermal medium or the gas of particle by some distribution function or particle density that give us a number of particles per unit of volume, per unit of momentum space. When we integrate over the momentum space, momentum of a particle in non-relativistic cases, it's mass time velocity. So basically it is the summation over all the velocities here. And Boltzmann found, he considered different quantity. I think it was this first term that is most important without the minus sign. So we today say that entropy increases, but he has the H quantity that was decreasing and it was approaching the minimum. And in his formulation of second law of thermodynamics, it was said that H decreases or entropy increases with time. It was derived from the quite basic assumption on symmetry of the interactions, even for classical particles like hard balls that collide with each other. But important assumption was the assumption of molecular chaos, or so-called Stoßzahlansatz. This is the assumption that number of particles that undergo the reaction with some two initial velocities is proportional to the number of particles of velocity 1 times the number of particles at the same place in space with velocity 2. So the initial velocities should be uncorrelated. And it is important to note that it is the temporal asymmetric assumption. So no wonder if we get some kind of error of time from thermodynamics, because we assumed that the particles were uncorrelated in the initial state and get correlated as a consequence of collisions. Thermal equilibrium in this sense is a state in which the entropy is maximal, so the derivative can be taken to be 0. And in this case, from kinetic theory, we can obtain that the distribution function takes this simple form. And important to note is, even for those who are not familiar with this stuff, is that this distribution has only two parameters. One is the chemical potential, the mu, which is kind of dummy variable that fixes the number of particles. And then there is temperature, which we know probably what it is, at least intuitively. Then we can have a more complicated case when there are more particle species. And they can undergo reaction, like A plus B particle goes to C and D, or vice versa, in another temporal direction. And when we talk about equilibrium in this case, we may talk about kinetic equilibrium, which means that all the particle species, all the components have the same temperature, or the chemical equilibrium, in which the chemical potentials at the beginning of the reaction have the same sum as in the end. The connection to the arrow of time, which I was talking about slightly, we have to be aware of the temporal asymmetry of the Stoßzahl assumption. And the arrow of time we perceive in everyday life is most likely to be connected to the low initial entropy in our universe. Thus, it is not a consequence of some weird interplay of particle interactions, most likely, but rather a consequence of the fact that we were born in kind of special universe, which has had a low entropy at the beginning. And there is a very, very nice book on the temporal asymmetry in general, and there are more arrows of time or more situations in which temporally asymmetric effects occur. The arrow of thermodynamics was mentioned here briefly. Then there is arrow of time in radiation. We all know that when we throw a rock into a lake, there are some kind of ripples and circles going out of that place, and not the opposite. There is the arrow of time in cosmology and in quantum theory, and all this is described to a certain extent in this book. It's a book for non-physicists, but it is good to have some background. The C, P, and T are discrete symmetries, so-called discrete symmetries, kind of reflections we have. P stands for parity, that I was already talking about, but there is a C symmetry, which stands for charge symmetry. Applying this symmetry to the world means exchanging particles and antiparticles, and vice versa. Then there is T symmetry, which is temporal inversion, like T goes to minus T, and vice versa. And all these are only approximate symmetries of the world. We can distinguish between T symmetric world and so on. But the combination, for good reasons, combination C, P, and T will leave the world unchanged. In the sense that it will not be possible to distinguish the behavior of such world. This does not mean that when I take the CPT picture of some kind of particle like proton, I will not be able to distinguish, like I will always be able to distinguish the proton and antiproton. But if I apply the CPT symmetry on myself and my experimental devices, then I will not be able to distinguish the situation. To describe the reactions in early universe, we need some kind of already mentioned kinetic theory. And this is described in terms of the so-called reaction rates. This is nothing complicated, in fact. The reaction rate is number of such reactions, like from some initial state I to some initial state F, per unit of time, per unit of volume. And these reaction rates inherit the properties of the interaction themselves. So when I talk about the CP or T symmetry, if I have a reaction that is CP symmetric or T symmetric, the reaction rates that will dictate the behavior of kinetic theory or the behavior of whole ensemble of many particles will inherit these properties. As I already mentioned, we have CP symmetric world, but the CP or T symmetry, which is the same, is broken. T is the same because it has to if there is breaking of CP, the T symmetry has to compensate for that breaking to have a CPT symmetric theory. So having a CP asymmetry is the same as having T symmetry, which is T asymmetry, which is given by this equation number 15. We define an asymmetry of a reaction rate, which is by definition reaction rate from initial state I to final state F minus the same for antiparticles in initial and final state, which is by the CPT theorem, so-called, the same as if I replace the final and initial state and make a CP transformation on that state. But what is important, that the interactions described by quantum field theory based on very, very fundamental assumptions such as locality, relativistic invariance, and CPT symmetry as a consequence. They have certain rules, and one of the rules is that sum over the final states, when taken over the asymmetries, will go to zero. So in equilibrium, the asymmetries of different reactions for a given initial state will compensate for each other. And this has important consequences, and the so-called Sakharov conditions that are necessary, the conditions, what is necessary to get the overabundance of matter over antimatter, or vice versa, in the universe or in general, there are three conditions of this type. The lepton or baryon number, or any other particle number that we are interested in, has to be violated in the interactions of our theory. There should be independent violation of charge symmetry and charge parity symmetry. And finally, all the systems have to be out of thermal equilibrium just because of this final relation. Because if it is in equilibrium, the asymmetries of different reactions will compensate for each other. In the standard model, or in cosmology, we can fulfill the condition of departure from thermal equilibrium. But we have not sufficient amount of C and CP violation. The only source of CP violation in standard model is kind of mixing between quarks. And it is not sufficient to produce the observed number of baryon asymmetry in the universe that we observe by looking at galaxies and the stuff we can see by telescopes. And there is no lepton or baryon number violation in interactions of the standard model. So definitely we have to add some new particles and new interactions to the standard model to explain by means of particle physics the origin of matter. So how we can get the out of equilibrium situation in the universe, in the expanding universe? How do we cut the universe into pieces? What kind of words we use? This, even though there is no reason for that, but somehow it happens that this is much less problematic than in the case of microscopic world of particles. Perhaps it's related to the fact that the building blocks or the object that we use for the description of the universe is given by means of optical observations. So the position and speed or velocity, these are well-defined terms at cosmological scales, even though we encounter some kind of problems coming from the fact that the speed of light is finite. So we always look into the past, far past. There are cosmological horizons that we cannot see to infinite distance. And general relativity is needed. All this is beyond the everyday experience, but it is still well working, and there are people who are specialized in this and have basically no problem to understand. An important assumption in cosmology is the so-called cosmological principle. The first step towards the cosmological principle was that of Copernicus, saying that in the center of the universe there is no Earth but the Sun. And continuing in this way, we get something that is called cosmological principle, basically saying that we have homogeneous and isotropic universe at certain large scales, and we can neglect the structures. This is nowadays justified by the observations, but it was first postulated in 1923 and 27, which is I think a short time after the nature of galaxies was understood. When we have a kind of problem from school that how deep dives the rubber duck in water, this is solved in terms of Archimedes' principle. But we do not have to consider the motion of every single molecule of water. We instead use an effective description of some continuum or fluid, neglecting the structure of the water. In a similar, of course, much more sophisticated way, we can neglect the structure of the universe, the stars and galaxies, at certain scales. And then, using the description in terms of general relativity, with its homogeneity and isotropy, we'll get an expansion of the universe quantitatively by this boxed Friedmann equation. A is the scaling parameter, which tell us how we'll change the distance of certain object. For non-physicists, that is important to note, the fact that the universe is expanding doesn't mean that we are expanding. Just the space between objects expands, because it is effect of at the large scales. That does not mean that galaxies itself expand and or so on. But all the objects moving freely in this universe slow down as a consequence of expansion of the universe. There is observational evidence for a long time here. The evidence of expansion of the universe. The left-handed plot on the left-hand side is the plot that was part of the Hubble's paper in 1929. And we can see that he put a line through the bunch of data for the closest or nearest galaxies. All these Hubble's data are just in this corner of the new plot, which is can be found in this article, the second one, from 1927. This is not the most recent, but the most beautiful I have found in literature. And this is the dependence of the luminosity distance, some measure of distance of those objects, the galaxies. And at the x-axis we have the so-called redshift, which give us how changes the wavelength of observed light during the travel from galaxy to the observer. We can see the departure from the linear behavior in the second plot. And the curve that can be fitted here is parameterized by these two parameters. First is Hubble constant, which is approximately the inverse of the age of the universe. And then there is the acceleration parameter, which measures the change of the speed of the expansion. The universe needs to have the same properties in all the spaces, neglecting the structure at the large scale. But that does not mean that it is completely flat. It can have a constant curvature, positive or negative. The different cases are shown in this picture with the two-dimensional space only. This is positive curvature, negative, and flat case. But the observation evidence shows that up to some experimental error, the universe seems to be flat, almost flat. The expansion of the universe is mostly given by the composition of the universe, the way the energy density in the universe, approximated by continuum, neglecting the structure, depends on the scaling parameter. And this can be found quite easily on the lecture on cosmology, perhaps. And this is the way how different components of the universe scale. R stands for radiation, which means photons and all the hot relativistic particles. They scale by a factor a to minus 4, basically, which is a to minus 3 for expanding of the space, expansion of the space, and one factor of I to minus 1 for the dilatation of the wavelength of the particles, which decreases or slows down the particles. Not slow down because if they are massless, it doesn't make sense, but decreases the energy. Then there is cold matter, which is slowly moving massive particles, which only scale due to the expansion of the space. So if we have the same amount of particles in certain volume and then we increase the volume, then the density of the particles is decreasing accordingly. And that there is something very weird. that has constant spatial density, and it is a cosmological constant or dark energy, quite mysterious thing. And what is very nice, that there are different independent observations that lead to the same point in this plot, which basically means that we have a picture that is consistent. Picture of the universe that is consistent, and it is a non-trivial thing, and it is perhaps the most powerful justification that what we do, or what the people doing this do, that it is right. The M component, which is I think 30%, is the matter which consists of baryons, I was talking already about, which are mainly protons. Neutrons are unstable, so neutrons can be stable in nuclei, but neutrons as a free particles have a lifetime kind of 15 minutes. But these baryons of omega B, which is something like 4-5% of the overall density in the universe, are stable, and this is basically the hydrogen. And then there is 26% of dark matter, particle dark matter, cold dark matter, that I will not talk about more in this lecture because it's for another lecture. Oh. The early and hot universe was dominated by radiation. Now we have only negligible amount of radiation here. It is not even shown in the plot. We have only matter and cosmological constant. But in the old times, just up to 10 to 4 years after the Big Bang, or up to the temperature 10 to 4 kelvins, the universe was hot and dominated by radiation. At this time, the temperature scaled as a to -1, and universe was cooling by expansion. So that means that if the universe expanded by a factor of 2, the temperature decreased by a factor of 2, or by a factor of 1/2. And this cooling of the universe is important, because when temperature, okay, I will start another way. I have already said that we need to extend the standard model in some way to get enough CP violation and to get lepton or baryon number violation. And one of the particle models is the so-called leptogenesis. That is based on adding some kind of heavy neutrinos, not the standard model light neutrinos, but the heavy neutrinos that can decay. An important feature of these heavy neutrinos is that they are their own antiparticles. They are heavy, up to the billion times the proton mass. And they decay into Higgs particles and leptons, like electrons, muons, or tauons, or the same but antiparticles. And this can be done by asymmetric way. So we have the violation of lepton number in interparticles interactions. The important thing, one of the Sakharov conditions. And the way how this becomes out of equilibrium, first it becomes out of chemical equilibrium, is that when temperature drops below the neutrino mass, the universe is cooling, and the decays are not compensated by creations of neutrinos. So all the heavy neutrinos will decay, and there will be not enough energy for cold leptons and Higgses to produce such heavy neutrinos. So this is how equilibrium is violated. Now, I cannot help myself. I have to talk a bit technical level. The reaction rate contains the so-called matrix elements coming from quantum field theory. And these are represented by squares of Feynman diagrams. And each Feynman diagram contains couplings and kinematics of the process. Some kind of weird integrals. The traditional principle how to compute the asymmetries is based on so-called Zhudkovsky cutting rules, the cutting, and give us some result in terms of imaginary part of the couplings and imaginary kinematics. what is not very nice at this traditional approach is that it is based on unnatural cutting of natural building blocks of the theory, the Feynman diagrams. And there are indeed, as a consequence, non-trivial cancellations of complicating expressions. Some miraculous zeros, if you remember from the beginning. In our recent paper, we proposed an alternative approach that is based on some kind of product of those Feynman diagrams. Example of those are here. In particular, these pictures represent the contribution to the neutrino decay asymmetry, the CP asymmetry of the heavy neutrino decay. These particular contributions are known in the literature, but the method proposed in our work is very suitable for higher order corrections to the asymmetries. So, made in Bratislava. And another important thing, which is perhaps too technical to be mentioned in this lecture in more detail, is the inclusion of quantum corrections to the description of the medium, like kind of quantum statistical physics. We started from the density functions in equilibrium, which were called the simple exponential, which were the so-called Maxwell-Boltzmann densities. But by summing this type of diagrams that are cut on a cylinder, we can obtain the full quantum dependence of those distribution functions, the so-called Fermi-Dirac or Bose-Einstein distribution just by this way, including correct cutting rules in thermal field theory, which we hope will be published soon in Physical Review D. And here is my summary, and I look forward to questions, if there are any. And thank you for your attention.
So thank you, Peter. Thank you, Peter, for a very nice colloquium. If there are any questions in the room, I ask you to bring some. If not, I do have some question at the very beginning. So if I understand correctly, you say that you are able to create the asymmetry in particle antiparticle abundance of matter simply by different way of cutting the diagrams, and you don't need any other particle into the standard model of particle physics itself. Did I understood it correctly?
Need heavy radiating neutrinos. These are new particles. These are not present in the standard model.
How heavy they are? So you need them.
They are expected to be heavy as I think about 10 to 10 GeV, which is 10 to 10 proton mass. 10 billion of proton mass.
Okay. Shouldn't we see them then?
No, because they are unstable. They all have decayed, and the energy is too high even for LHC. They cannot be produced even at LHC, because LHC can produce particles up to the masses of some thousands of GeV, not to some kind of billion GeV.
Where we could see their...
we cannot see them. We can assume them and work out the consequences.
Okay, thank you very much. I see there is another question coming, please.
It's very interesting topics and presentation.
Thank you.
So when you say we cannot see them, my idea is that maybe we can see them in neutrino telescopes by production. You can have a light neutrino which interact with the medium, with the water, and then you can produce heavy neutrino.
But even
because the energies are PV.
Okay. So, but this should be extremely rare event.
Rare event, but we are looking for it.
Okay. So here is the more correct answer, perhaps.
We hope to see something like that, but not really till now well addressed this subject. But so your assumptions, how can you fully explain the matter-asymmetry of the universe due to CP violation in the lepton sector,
Mm.
and how it depend on the scale and
There is important thing that I was not talking about, but this mechanism will first produce a lepton asymmetry, the asymmetry in the lepton sector at the high scale of the seesaw mechanism. And then during the electroweak phase transition, there will be kind of processes, the so-called Falenon processes, that will generate the asymmetry in the baryon sector, the opposite asymmetry. So then we have a, which is good thing, because just due to the electric neutrality, because we have some kind of asymmetry in lepton sector and the opposite asymmetry in baryon sector.
But there can be also different type of seesaw.
Okay. So there are very many other models. Like for each seesaw, there is model of leptogenesis, as far as I know, and there are other extensions of the standard model and other mechanisms of leptogenesis. This is based on decay of out of equilibrium decay of heavy particle, and then there are mechanisms based on scattering processes that become out of equilibrium.
Okay, maybe we will discuss later, because I assume there are other people that would like to ask something.
But to be honest, I'm not specialized on particular mechanisms. What I'm interested in is the mechanism or method of calculation of the asymmetries and thermal corrections. Okay, thank you for the question.
Thanks a lot for a nice talk. I have two questions that maybe you have already answered, that I have missed the thing in your presentation. If yes, I'm very sorry. But the first question: where does the mass of the heavy neutrinos come from? How do we know how heavy they should be?
I think it's put explicitly into theory as a parameter.
But how do we fix the parameter? Like
the parameter's value or the limit on the mass comes from the light neutrino masses. Just by assumption that the couplings of the theory have to be of order 1, there shouldn't be any kind of fine-tuning of the couplings. And then by the so-called seesaw mechanism, the scale of the heavy neutrino masses is fixed by the low neutrino mass.
Okay, thank you.
That is known.
And the second question is, where do the heavy neutrinos fit into the standard model particle table? Is it a new family of particles, or is it a new column or a new row?
I will look at the table of particles here. It's more complicated, because in fact each of the particles here should be twice there. There are two top quarks, the right-handed or right and left-handed, or right chiral and left chiral. So it should be put perhaps behind the table of particles.
Yes, but it follows already from the fact that in the standard model the masses of neutrinos are 0. So masses mean there should be some another new generation of neutron masses, not like in the standard model, and it determines the scale. So within the Weinberg effective theory, we assume there is some new scale which is associated with lepton number violation, and it's just important for this asymmetry. So we don't know where is the scale, but the people assume, like Weinberg, that there are such, for example, 5-dimensional operators which are responsible for neutrino masses. It's physics beyond the standard.
Okay, thank you.
I still have one question, but I probably tend to explain it to myself during Euro has asking his. You need the neutrino to be unstable in order to decay very soon. It came to my mind like why it cannot be a candidate for the dark matter? Is this
it's
the
unstable
reason? Because it's unstable and decays very fast.
And it's
so these two things are, because also for the dark matter candidates, people say that it could interact weakly and so on. So these are two different mechanisms that cannot match.
In this particular mechanism I was presented here briefly, the neutrino cannot be dark matter candidate because it's heavy and unstable. But sure, there are models in which the sterile neutrinos are good dark matter candidates, but I'm not sure if there is not some kind of problem with cosmological observations, like the galaxy formation and so. Perhaps there is already some tension of these models with observation, but I'm not working with this.
Understand. Let me please check the chat if there are. No, I don't see any questions in the chat. Oh, yeah, sure. I see. I have a question on the right side plot in the slide where equation 19 is provided. In the right-hand side plot there, is the light blue line the best fit line of the data, because it seems that in the end that the line is deviated from the data points.
It is the line. As far as I know, the dependence in this plot should be described by the equation on the very left side of equation 19 here. This perhaps Vlado Balak will be more better, but this green line corresponds to the first term here.
Yes, because already in the second term,
this term measures the deviation that is not fitted in this picture. Yes. And it is interesting, the interesting part of the picture, the deviation from the linearity.
So one more time, do I understand correctly that this first is linear term coming from the redshift with the Hubble constant?
The green line,
yes,
is plotted the first term here, the z.
The z. And the second one are the corrections coming from,
yes,
okay, with the z squared and so on.
Yes.
So
and the second term is probably sensitive to what we call the dark energy.
Yes,
which causes the acceleration of the universe.
Yes, which probably we see over here as the curve is going up with rising redshift and the bigger distance over the linears.
There was on the next slide, I think there was this value of Q0, or no, it was the one slide before perhaps, yes, Q0. So that this value should fit this curve which is bent upwards.
So please, if you take this value and put it in the equation on the slide before and draw the line, you should fit all over the data.
And interesting thing here is the minus sign, which means that the universe is expanding, accelerating, and not decelerating. The Q is historically called to be deceleration parameter, but the negative sign means that the universe is accelerating, which is new thing, I think, from WMAP data in 2000.
No, it first came from the observations of supernovas of the type 1A.
The author of the question, Khatum Amina, thanks us very well. So I think we explained the question. If there are any other questions, please. I see.
Just a comment. So you need actually 3 neutral heavy fermions, yes?
I don't know if they in minimal model.
Because if you have just seesaw, you can just neglect this coupling of light and heavy sector, and then for CP we need matrix by 3 by 3. I
need more than one, at least.
No, you know, you
I
have
think
like
minimal model.
Check matrix, and you have just Cabby angle. If there will be only mixing matrix, would be 2 by 2. There is no phase. Yes.
I need irreducible complex phase, and I'm not sure if there. I have seen models in which only two generations were present, but probably it was based on something different. So basically, what I need is to have irreducible complex couplings and sufficient amount of intermediate states that cause the CP violation.
Okay. I have to see
because of when you consider the I don't know where it was the condition the cancellation of asymmetries, I need to have sufficient amount of final states. Because if there is not, then each single term has to be 0. And it is determined by the structure of the couplings in the theory.
But then it is related to seesaw, yes? This,
okay, it's particle model where we have 3 generations of neutrinos.
So I'm just more interested in there is a CP violation in the heavy sector.
And of course, the heavier generations of the right-handed neutrino or the sterile neutrino have to be of different mass. They shouldn't be of the same mass.
Okay, thank you very much for all of the questions. Thank you very much, all of you, for joining us. Thank Peter one more time, please, for his energy and time divided to this colloquium. And in this manner, we should end up for now, and we can see each other next time. Thank you very much. Goodbye. Have a nice evening.